Okay, everybody, let's get started. So I sent out an announcement about the project, a couple of updates. So I realized that there was definitely the instructions are a bit scattered, and for those who are not comfortable with the command line, and there were lots of different ways to install the virtual machine. And so there was a lot of people had issues like getting the project submitted. So I'm gonna just like waive the late penalties for 2 weeks so that everybody can just sort of get situated. Also, at the recommendation of one of your classmates who's sitting over here in the front, I updated the README for the projects to just have a big long list of all of the commands you need to do, roughly in order from start to finish to set up your project. Because everybody has kind of a different installation, I just assume that the repositories are in your home directory. But for those of you who use Vagrant, your repository might be in the /Vagrant directory. So you can just kind of substitute that in when you're reading these commands. But if you need to remember how to do anything like tag your project and submit it to GitHub, or do adds and commits, or get the make file, then this list should cover most of it. Please send pull requests if you find anything missing or incorrect. Okay, so there's that part. Oh yeah, and there's a section on how to actually see what the grader will see. So this last section, sanity check your repository. You can just clone a fresh copy of your repository in your temp. I just put it into the temp folder, which on most Unix systems you're going to have. And then so do clone a fresh copy there. Check out the tagged version, and then you can run make and do all your testing. And that's why you can see what the grader will see. In addition, there are now the grader scripts online and available to use. They might still be a little bit rough, but they work for me when I tried them, and I can actually give a little demo of them. So this is another repository called grader-scripts. It's a public repository. What's that? Oh, because it's not mirroring for some reason. Don't know why that happened. Say, yeah? Are there instructions on how to run the scripts? Yes. So there's a README here. So hopefully you all know this README style. Every open source project should have a README file. And just look for that when you're looking at other people's source code. You will have to install make sure Python 3 is installed if it's not already installed on your machine. And you just basically, here's how you clone the repository. You can go to your home directory, typing cd, enter will just go to your home directory in any Linux or Bash shell system. This is how you can clone the project. And then to actually run it, it's fairly straightforward. You just go into your cloned repository, which I'm assuming is in your home directory, but if you're using if you have it in that Vagrant, on your host machine, then you'll change directory to that. And then you just run it like this. Python 3 is the Python interpreter, the script name, which ... So who here knows what ... is? Who knows ... Who doesn't know ... Oh, interesting. Okay, so ... just refers to the parent directory, and dot refers to your current directory. So this is like classic Unix shell stuff. So ... says go to your parent directory and go to the grader scripts directory. So this is assuming that your project and the grader scripts are siblings in the same file system. So you run that script. This says where your project repository is. It's currently the current directory. That's what / means. And then give it the path to all the test cases. So in this setup, if you follow the README from the projects directory, the syllabus repository, your repository, and the grader scripts will all be in your home path. They'll all be cloned in the same place. But if you're facile with using these paths, you can just substitute wherever on your file system that you have these stored. I know a lot of people are used to using the graphical interface, but I like the command line because it exposes you a little more to how the file system is actually structured at a little bit of a lower level. Okay, so that's how you run it. So let me show a little demo of running it. So I have my test directory here. This is my phony project. And to run it, because I don't like to memorize command lines, I can just cut and paste. So let's see what happens. So you get quite a bit of output. The nice thing about this output that I give you is that it is the actual commands that are being run to test your program. So the first thing that gets run is make, and it checks to see if your program builds. And the next thing that gets run is this long command here. It runs this compile.sh script, which is now inside the greater scripts repository. It passes the name of your compiler, /simplec, current directory is where it is, and the path to a particular simplec file. And it just checks to see whether that command had an error or not. It didn't, it passed. Then it tries to run it. That passed. So then it does a diff, which just means comparing the ground truth file to what your program actually output. Spacing.out here. Make this a little bigger. And that moved my cursor down. So this is the line I was looking at. And now if your program fails, you can just cut and paste this one, wherever it failed, you can cut and paste the command that was run when it failed. So for instance, if in order to make it fail, I'm going to alter one of these ground truth files just to cause it to fail. Don't actually do this. So I'm just going to modify the subtract test case output. So now when I run the greater scripts on this, you'll see it was successfully your compiler successfully ran. There was no seg fault. It successfully ran the output program. But then when we did a diff, I should not say passed here, but there was an error here on the diff. So you can run any of these commands to replicate the process of doing this grading. So for instance, if I run this diff command, where's the failed one? So it was subtract that failed. It failed on subtract. Uh-oh. I may need to correct this script a little more. But in the future, you'll be able to just cut and paste these commands. Okay. Well, anyway, so I'll repair that tonight. But any questions on this? You kind of get the idea. So you just run the script, and it'll tell you whether each case has passed or failed. Yeah. And then there's instructions on how to run those individual scripts as well. It actually worked here in my output, but. Okay, so that's the greater scripts. So those should be available. They'll be upgraded as the semester goes along. The penalties waived for 2 weeks. You have a way to actually check what the grader sees and actually run the grader scripts. Okay, so I think that's pretty much it for like setup and tooling. Hopefully most people I seem to be pretty much settled in. I know this was like a lot of tooling to be dumped on you, but hopefully in the future when you go become a software engineer or something, you'll remember back and remember what I was talking to you about version control and what you struggle through on the command line, and hopefully it'll make you a better programmer in the future. Any questions on this? Any questions on the tooling, the setup? Does anyone still have issues? Who still has issues where like you can't get your project submitted or you can't get your virtual machine running? Okay, so of the people here, I guess, who want to admit it, of the people here, everything seems to be okay. All right, so let's get into the new material. So last time we looked at recursive descent parsing, and how we can modify our grammar so that we can not only do recursive descent parsing, but do predictive parsing. So does anybody remember what we had to do to the grammar in order to enable recursive descent parsing? Yeah. Yeah, exactly. We had to make it a right recursive grammar instead of a left recursive grammar. And the problem is illustrated on this slide, so recursive descent parser works by taking each production in your grammar. So productions just take non-terminals to some expansion of symbols. And with a recursive descent parser, we just take each one of these productions and turn it into code, where the left-hand side of the production is the name of the function. The right-hand side is the body of the function. So for instance, for program is a 0 or more statements. So we just make a new function, a new parsing function for the program construct that consists of code that just reads 0 or more statements. So factor, for instance, there are two different possible productions. So we have one function called factor that parses a factor construct, and it checks to see which production which production is being expanded based on the next token in the input. So if we see a left paren in the input, then that tells us we're reading the first production, L paren, expression R paren. So in our code, we actually just check the next token in the input or the next character in the input, and then just recursively call all of the symbols on the right-hand side of that production. So we just recursively consume a left parenthesis, and then just consume the left parenthesis, and then recursively call an expression to start recursively parsing that nested expression. And that's going to take us back to a different place in the grammar. We'll reach factor again. If there's other nested expressions, then those are going to be recursively processed. And so there's this very tight relationship between context-free grammars and recursion, because they all have this nested structure. All right, any questions on this so far? Just recursive descent parsing? The concept of it, at least? Okay. And as your classmate pointed out, if we have left recursion, then we can end up with a situation where we just have an infinite recursion that doesn't actually parse the input. So if we just kind of blindly turn every production into a set of recursive functions, we may end up with a parser that doesn't actually parse. And the kind of intuition behind this is that we don't really know which production to apply here. We have to do something extra in order to figure out which production, in order to basically have a base case to stop the recursion. So what we did is we did left recursion elimination. So we turned our grammar for expressions, for instance, we took that left recursive grammar and turned it into a right recursive grammar by adding this new non-terminal expression prime. So expression prime is now right recursive because the last symbol is referring to itself. And so basically what we did is we took if we look at how the Dragon Book shows it, we took the suffix of the production, all the stuff after the recursive part, and turned that as the prefix of a new non-terminal. So this A prime, the prefix of every production in A prime, is the suffix of the original left recursive grammar. So it's literally just taking left recursion, turning it into right recursion. But there's a little extra bookkeeping you have to do for the productions that were not left recursive, and that's kind of what all the other extra productions are here. Okay, so that was your homework. I think it was due today. Is that the homework due today?
Yeah.
Or maybe that's the homework. No, maybe that's the homework due Thursday.
Turning from left to right.
What's that?
Turning from left to right.
Yeah.
That's Thursday.
That's Thursday. Okay, that's Thursday. So maybe some of you have done this. Operator precedence was the one due today. Okay, so anyway, it's a little like busy work, sitting down and crunching through this, just kind of applying this pattern to do this transformation. Okay, so now that we have this grammar, we can implement not only a recursive descent parser, but we can implement a predictive parser. Predictive parser just says we can determine exactly which production comes next based on the next token in the input. We'll talk about this a little later in the semester, but not all grammars can be turned into predictive parsing grammars. But the grammar I've given you should be able to just do, should be able to work with predictive parsing. It's convenient because you basically get a linear time parsing algorithm, even though you have a bunch of recursion. But anyway, today I want to go over more into this recursive descent parsing, but also show you how code can be emitted as we parse. So as I said last time, I really strongly encourage just getting the parsing right first. Like write these parsing functions and test it on input files just to see whether you get a seg fault or whether it actually successfully runs. Now, just because the parser successfully runs doesn't mean it's actually parsing the right input. But if you start by kind of doing a literal translation of these grammar constructs to functions, then you should, it should be pretty evident when your parser is broken. Has anyone who's actually started writing the parser? Has anyone started writing the parser? Oh, very few people. Okay. Who has not started writing the parser? Oh, okay. Okay. So I would recommend doing the parsing first and then adding the code generation. The code generation really can be added later, and it's pretty tricky to try to do both at once. Because if your parsing is messed up in any way, the code generation is just going to be wrong. Okay, so let's. So questions on any of this, like context-free grammars? Yeah. Write recursive grammars are for recursive descent parsers. So you'd use it for that. But I'll show you another parsing algorithm next week that handles left recursion. You can have this kind of more natural specification of an expression grammar, and it has no problem with left recursion because it's not recursive descent. There's other parsing algorithms that don't have this sensitivity to left recursion. For your project, I'm recommending that you use this predictive parser, this recursive descent parser. But next week, I just want to show you another parsing algorithm that can actually handle more grammars, like left recursive grammars. But it's a little more hairy to implement. It's a little trickier to implement. The recursive descent parser is, believe it or not, is like the easier parser to implement. It's all pretty tricky to implement parsing, but recursive descent is kind of a maybe more natural way because it kind of looks like the grammar when you do it. And it gives you really good practice with doing recursion. Yeah?
Of the two parsing techniques you're showing us this week and that next lecture,
yeah.
Which are the ones more commonly found in languages that we code in C?
Oh, that's a really good question. I don't know all the languages. GCC used to use the kind I was going to show next week, a table-driven bottom-up parser. But they actually switched in version 3 to a top-down recursive descent. Clang, which is the LLVM's C compiler, the C compiler that generates LLVM, that I think also uses a recursive descent parser. So they seem to have, I don't know, maybe they reemerged as being more popular choice. But yeah, I don't know overall in languages. I'm not sure. But yeah, for C, those are the two biggest C compilers, and they're both recursive descent at this point, as far as I remember. No, that's a good question. Any other questions? Okay, so let's look at code generation. So this is mostly going to be kind of Blackboard class, mostly demos, but I'll just give a quick sort of introduction to what the problem is and what we're trying to accomplish with code generation. Okay, so in project 1, I gave you a simpler grammar where statements can only have a single operation in each statement. It's either going to be addition, subtraction, division. There's no nesting of expressions. But in probably most of the programming languages you use, like C and Java, they allow these arbitrarily large expressions. And as we saw with context-free grammars, we need a more rich formalism, a more powerful formalism in order to be able to describe these kinds of languages. And so we went through all this rigmarole with context-free grammars and how you do parsing and how you look at the structure of input and how you just take a sequence of characters and sort of infer what the structure is just from the sequence of characters. But then the next problem is, even if we can have this nice recursive descent parser that can recognize that our input is grammatical, how do we actually use that to generate code? LLVM and machine code, they don't support arbitrary expressions. They can do, if you remember from CDA, each assembly operation just does like one addition or subtraction. You can't just give it some arbitrarily large expression. So what our compiler needs to do is take that structured input, that structured syntax, and somehow convert it into just a sequence, a linear sequence of machine operations. And the main trick behind this is that we make temporary variables. We use a bunch of temporary variables to store the intermediate results as we're computing an expression. So if we have -5 plus 2 times 3, we have to compute 2 times 3 first. So here's an example. So if we have, is this thing cutting out?
Yes.
All right. You can feel free to tell me if this is like, let me try this one. Okay, hopefully that will work better. That one's louder too. Okay, so if we have like -5 plus 2 times 3, remembering our operator precedence, the 2 times 3 happens first. So one way to compute this arithmetic expression using machine code or IR is to do the 2 times 3 first and store it in a temporary value. So here we're storing it into T1. And then we just do the addition using that temporary value. So now we've got -5 plus T1, our temporary value. So that's really the main trick here, is that we just take some nested sequence of expressions and just turn it into a long line of machine operations. And this is basically what you do like in your head, or if you have some complicated math expression, you like sit down and work out all the intermediate values. If you had a desktop calculator that can't do parentheses, you just sit down and work out each operation one at a time. It's the same idea. But in this case, you're writing a compiler, a machine that can actually do this conversion automatically. So questions on this? Any questions on the LLVM IR? Hopefully it looks somewhat familiar at this point. You should all be experts now on LLVM. But it's the nice thing about this project is it doesn't require any extra LLVM IR. Everything you learned and used in Project Zero can just be used for Project One. You don't need any extra IR instructions. The only difference is that now operations will not just take two constants, they'll take a constant. They can take variables as well. That's really the only difference. Okay, so just a review of our predictive parsing grammar. So this is due on Thursday, and go over it, go over the homework, go over the lectures. This is what the expression grammar now looks like. We have an expression expands to term followed by expression prime. Expression prime is our new right recursive non-terminal. Expression prime now starts with plus or minus. I've trimmed this grammar down to fit on a slide. So there'll be a production that starts with plus, is followed by term, and then has our right recursive call to expression prime. Or the production can just be empty. So if you imagine we have -5 plus 2, then the expression term will cover -5. Expression prime will cover plus 2. The plus is covered by this terminal, and then the next term is going to be 2. So expression prime will just be epsilon. And I'll show another example of this. So here's our new right recursive grammar that has operator precedence. And as I went over, the predictive parser is able to pick which production to expand at each step of the of parsing for each input symbol. So questions on this? Any questions on this? All straightforward, right? I cover this. And then with recursive descent parsing, I covered this already. But here's what the algorithm will look like. I think I haven't shown something like this yet, but this is what the algorithm will look like for recursive descent parsing on the right recursive version of the grammar. So remember, the expression expands to a term followed by expression prime. So in pseudocode, the body will literally just call the term non-terminal and then call the expression prime non-terminal. For expression prime, because there are many possible productions that expression prime could expand to, we use the look-ahead token, which I just call next here, and say if the next token is a plus, then we consume that token, which just means read it in and move to the next token, and then recursively call a term and recursively call expression prime after it. So it's just a straightforward conversion into pseudocode from the grammar. Otherwise, if we don't see a look ahead that matches any of our productions, we do nothing. And factor is not recursive, but it does have multiple productions. So it can either be parenthesized expression or just a number. So we just check the next token and check whether it's a left paren or a number, and then just consume tokens and recursively call functions. So any questions on this? Pretty much covered this last time, but any questions? All good? So you can kind of use this slide as a little hints at how you can write your parser. Okay, so here's where it gets interesting, adding code generation to this parser. So I've highlighted in red here. I didn't do the full grammar, but just for expression and expression prime, I've added in red where the code generation stuff will happen. So having this right recursive grammar makes the code generation just a little bit more complicated. So I had to sit down and work it out and make sure it's right. But the basic idea is that because the expression, if you have -5 plus 2, that's kind of broken up into two different productions. So the expression just has the left side of the operation, and expression prime has the rest of the operation, has the +2 part. So in order to make that work, pass in the left-hand side that was recognized by our expression by calling term. And then expression prime is what's going to emit our operation. So expression prime now has the left operand, and its job is to read plus and the right operand. So assuming that the next input is actually plus, then it's going to figure out what the right operand is by calling term. It's going to create a new temporary variable, because we need to do that to have, we need to store intermediate values, and then just emit the LLVMIR for doing the addition, saving that, emit the code that actually says, add these two left and right operands and store it in our new temporary variable. And then for reasons that'll become more clear when I show an example, this result is actually passed to expression prime. And we'll see, that handles the kind of nested expressions, and I'll show that. And if it's epsilon, that means there was no plus whatever. It means expression prime didn't actually have an operation, so we just returned the left operand. Okay, so I probably have lots and lots of questions on this. So to make this clear, let me go through several examples of what code generation will look like, and we can kind of build up these functions, these parsing and code generation functions as we go along. So let me get set up here. Okay, let's start with a very simple example. Let's start with the input just has print -5 semicolon. Say we're just parsing and generating code for that. Now I know in Project Zero you did this already, but let's see how we do this using the general solution for any parse tool. So let's assume that we've already, we just started parsing the expression itself. So I'm not going to start at the top of the program. Well, actually, let me just show the top of the program. So there'll be program at the root that will have some list of statements. And inside the statement, you read print, you read some expression, and you read a semicolon. So now let's do the parse tree generation for the expression node. Okay, so what is the first production? What's the production that we choose to expand expression? If anybody remembers or ideally has it in front of you. Do you want me to show you the grammar again? All right. So let's do it this way. What's that? TE prime. That sounds right. So here's our, it's a little small. So it's a little small, but the expression only has one production that could possibly be expanded. And so it's term and expression prime. And then what can term expand to? So factor term prime. So term can only expand to a factor and a term prime. And the only option we have for factor is -5. That's the end of our expression. So E prime must have been the empty string, which is one of, that's one of the two productions that we have. So this is the parse tree for just the -5 expression. Let me actually put the grammar here. So I'm going to use the drag and hook notation for the expression grammar. E is expression. The arrow means production. T is term. Plus, wait. Sorry, I messed this up already. Just give me 1 second to write this out. Okay, so on the right hand side we have I put the grammar, but kind of in the drag and book notation, so it's a little easier to write. Questions on this? Any clarification for this version of the grammar? So it's the same thing that I showed in the slides, but it's in this like formal drag and book notation. But please let me know if you have questions about the notation or if it's not clear. So just using this version of the grammar and forgetting about the entire statement, if we've got -5, then as we walk through, if we're starting at E, then the only production that we can expand is TE prime. T can only expand to FT prime, and F must have expanded to a number, which matches our input 5. Because that's the end of our expression, the next character is going to be a semicolon, then T prime must have been epsilon and E prime must have been epsilon. With me so far on this? Are you guys with me so far on this, like just generating the parse tree for this?
Would the 2 prime and E prime function calls be basically saying if this is a semicolon and just returning null?
They can do something simpler. They can say, is it like for T prime, for instance, they can say, is it a multiplication sign? Is it a division? Is it a mod symbol? And if it's none of those, then we know it must be epsilon.
What do you typically return when you hit epsilon, since most of these are returning like the
That's a good question. We'll get into that. We'll get into what the return, how all the returns work. So let's look at that. Let's look at that now, actually. And any questions on the parsing, the parse tree stuff? Nobody? Okay, what's that? We'll do other expressions. We'll do other expressions besides this one. So just to illustrate like the code generation part. Okay, so ultimately all that we want is like -5 to be printed out. But with this parse tree, how do we do that with this parse tree? So ultimately, we want E to return -5 to its caller. You know, a statement is what calls expression, and statement is going to be generating the code for printing. So ultimately, we want -5 to be returned by E. Questions on this? You with me so far on this? So ideally, when we call E, it's going to tell its caller that we ended up with -5. So how did this happen? So T, we would also want to tell its caller that it passed -5. And similarly, we hope that F will tell its caller that we passed -5, because F is what actually saw the token. So once it reads in that number token, F knows the exact token that was read in at that part of the input, and it can just tell its parent that I saw -5. Then T can say I saw -5 and pass that back to E, who can then tell the statement I saw -5. With me so far on this? With me so far? So that all seems like fairly straightforward. We know now that F and T and E, they return something. They're going to return some value or some variable. But this gets a little bit more complicated when we have more complicated expressions. So questions on this so far? Questions on this? Is it okay if I erase this one to leave the grammar? I want to leave the grammar here. Can I erase this one? Okay. So let's do the parse tree for -5 plus 2. Let's put that nice and low down here. -5 plus 2. All right, so let's real quick do the parse tree for this. So we've got, so E, we start at E at the top. And what's the first production that gets expanded for E? Call it out, yeah, T, E prime. So in this case, for, let me give a little more room to myself here. So T E prime. Now, what about T? What does T expand to? Must expand to F T prime. F must match this input number here. So something that I'm sort of glossing over is that there's, when you have your look ahead and your input token, F will actually consume -5 and advance the look ahead to plus, so that when we start looking at T prime, so what does T prime expand to? Does anybody know what T prime expands to? It expands to epsilon because T prime can only match multiplication or division or modulo. So if we see a plus in the input and we're parsing T prime, then that means we can't consume any tokens. The only production we can match is the empty string token. Questions on this? You with me so far on this? Okay, so now we're at E prime. So E prime, we have several productions that we can choose here. The next token in the input is a plus, and we see the E prime production. So next token input is a plus, and we see the E prime non-terminal. So how do we, which production do we pick for this? We see plus in the input, and we have two possible productions to choose from. So which one is it? It's the plus, right? We see plus, so we expand this plus T E prime production. So that gives us plus T and E prime. And now we've got T again. So T has to expand to F T prime. And F, we see a number in the input again. We see 2. So F consumes the number 2. And T prime now sees semicolon in the input. So what production do we expand when we see semicolon in the input and we're parsing T prime? Epsilon. It can't match, it doesn't match any of the productions, so we know that T prime must match epsilon. And similarly, we see E prime, we're parsing now E prime, and we see semicolon in the input. So what production must we match? Also epsilon. Okay, so there's our parse tree. Let's look at how we can construct, automatically generate the IR and how we sort of bookkeep all of these values as we're recursively processing this tree. Okay, so just like I think you probably did with like infix to postfix, you do this tree traversal, this post-order tree traversal. So post-order, what is post-order? Anybody remember post-order tree traversal? What's post-order tree traversal? A little review. You go to the left and then the right, and then you process the root. So if it's just printing, you print the left one, you print the right one recursively, and then you print the parent. It's post-order because the processing of the parent node happens after. That's why it's post-order. Pre-order, the other way. So for processing these expression trees, the like semantics of the expression trees is that we do a post-order traversal of this tree. Now, if we had our left recursive grammar, processing this tree would be a lot easier actually. But with this right recursion, it makes the code generation a little bit more complicated, but not too much more complicated. All right, so what's the first node we process when we're doing this post order? -5, yeah. So we start at E, and then we recursively call its 2 children. So when we recursively call T, we then have to recursively do our post order traversal. So we end up calling F. F is the first leaf that we encounter. So F reads its token and sees that it's -5, and it passes -5 back to its parent. Okay, now even though we know that T prime is going to be epsilon, it won't necessarily always be epsilon. So what I'm going to do, and we'll see why this happens later, is I'm going to actually pass what -5 found as its left child, pass that to T prime. And we'll see why in a second why we do that. But because T prime is epsilon, it has no syntax under it. It's just going to pass -5 back to its parent. Now that seems kind of pointless, right now, but it'll make a little bit more sense once we get to E prime. Okay, so now T has finished processing its subtree, and it has discovered that the value of its subtree is -5. Right? That's all the syntax that was in there. T now has finished processing this side of the tree, and it has found that its value is -5. Okay. So like with T prime, E now knows its left operand's value, but it doesn't know its right side's value. And not only that, it doesn't know the right operator either. So really here, what we're going to do is E prime is what's going to handle the addition operation. So E is just kind of a proxy for passing the left operand to E prime, because the actual plus symbol is under the structure of E prime. So in order to allow E prime to do the arithmetic operation, E is going to pass the value that it found on the left-hand side to E prime. It's as if E prime was the root node, and the left child was E, and the right child, was what we're gonna compute next. With me so far? So we'll see how this works out as we continue computing this. All right. So now we're on E prime. E prime sees that it's an addition operation. So we need to remember that, okay, we're doing addition, or we just need to, so if we have 2 separate productions, one for plus and one for minus, we can either record the operator, or we can just have 2 separate productions for it. So we just consume this plus operation, and now we need to know the value of its right-hand side, the right-hand side of the addition operation. So to do that, E will first call t. It's not going to pass anything to it. It's just going to call t because now we're starting to compute the right-hand side of our plus operation. So when we start computing t, what happens when we call t? T now looks to its left child to see what its value is. And what does it get from its left child? What does it see the value is for its left child? It sees 2 as the left child. So f consumes the 2 token and tells its parent t that its value is f, or this value is 2. So similarly, as we saw before with t prime, t will pass this value to t prime because t prime is really what could be doing the operation. T here, the reason is that t does not know what is under t prime. We don't have to do any kind of fancy algorithm here. We can just assume that t always assumes that t prime could have some operation in it. So t passes 2 to t prime. T prime has no operations under its tree, so it just passes 2 back to t. Okay, here's where it gets a little bit more tricky. So t knows that its value is 2, but we could have a stream of more operations to the right. It's possible that this could have been 2 plus 3 plus 3 plus 4 plus 5. It could be some string of an arbitrarily long string of operations at the same precedence. So to handle operations at the same precedence, we just compute the leftmost operation first, compute that value, and then pass it on to the right tree in order to continue computing. And we'll see another example of having, we can see an example of having multiple operations that have the same precedence. But just like we did for the root node, E prime will pass what it knows to be the value of its left-hand side. Oh, actually, I'm sorry, I skipped a step. Okay, sorry, I got a little bit ahead of myself. So now E prime, what does E prime know at this point? E prime knows that its left-hand side of the addition operation is -5, and it knows that the right-hand side of the addition operation was 2. So it has both operands here. E told it what the left operand was, and T is the right operand of the addition. Because -5 was tied to the left side of E, and +2 is seen in this subtree. With me so far? Questions on this? Yeah, questions? No? So you can see that +2 is entirely contained, or plus is entirely contained in E prime's right child, and the left operand was given to it by E. So if you sit down and work through it, it'll make more sense, or rewatch the video, watch me kind of stumble through it. But it's good to just kind of sit down and work through it. All right, so now E prime knows its left operand and its right operand, and it knows that we're doing an addition. So now what can we do with this information? We can create a temporary variable and actually emit the addition operation at this point. So at this point, E prime can create a new temp variable. So let's call it T1. So it can create a new temporary variable T1 and actually just emit the operation. It actually can just spit that out. So if I save the code that's being emitted, that's what E1 just immediately prints this out. And this is the first operation that will be done in our compilation. Okay. So now that it figured this information out, it's going to pass T1 to E prime. And this is because E prime doesn't know what's to the right of it. It doesn't know if there's more operations to come after -5 + 2. So it just kind of proactively passes its new value. So E prime's new value is T1. It's that T1 symbolizes the result of the operation. So it passes on this new variable to E prime, but E prime has no syntax underneath it. So it just passes what its result is, which is still T1, back to E prime. E prime passes this back to E, who can then give it to its parent, to be printed out. Questions on this? Yeah.
So when you create LLVM increments, would you just have to read through the expression like T1 that you return?
When you want to emit LLVMIR?
Yeah. So now that you have your expression versus the set, I used to read through it.
So this is what you emit. So you emit this thing in LLVMIR. So you'll actually emit like T1 equals add, NSW.
That's what you meant.
Actually, let me show the next example, and it'll make it clear why we're passing these result values around. Because maybe that'll answer it. Yeah. What's that? Say again. It turns out that you can just keep a global value that has the number of your temp variables and just increment that globally, because the tree enforces the order of operations when you do a post order. So you can just you just say give me new temp variable. That you just want a new temporary variable, and a quick way to do it is just always increment a global counter to do it. Okay, so I'm going to defer my answer and show a yet more complicated example. So questions on this one so far? Questions on this one? Okay. So let me delete all this somehow. Wow, interesting. An oversight. What? Why is it undeletable? Wow. No.
What happened?
Oh. I deleted the note instead of the figure.
Oh no.
Let's see if I can undelete it. No. Almost hit the wrong button. It's really funny that it's very hard to just erase this en masse. But, oh well. Wow. Let's just do this. Out of sight, out of mind. All right. Okay, so let's look at a more complicated example. The example with two operations of different precedence. So let's look at -5 plus 2 times 3 now. So which operation comes first? Multiplication, yeah. The multiplication comes first. All right, so let's quickly do this parse tree. 1, 2. Make sure I give myself enough room. So I'll just write this parse tree out, since I think hopefully you more or less know how to do this. So now this time, T prime is not empty. T prime matches the star F T production. And my handwriting is a little ugly.
Isn't there a E prime after the T with the plus?
An E prime
Yeah.
after T?
Yeah, like when you consume the plus, isn't it plus?
Oh, E prime. Oh, yeah, plus.
It's
Good
probably
call.
gonna be
No, you're right.
Anyway,
No, but you're right. Totally right. No, that's important. So F T prime and then T prime is empty. Is that right? Did I miss anything? Anything else I miss? E prime is empty.
That's sort of what I got, yeah.
Okay. Yeah, any issues with it? All good?
I got that.
All right, so just like before, F is going to tell its parent that it's all -5. T is going to tell its child that its current value is -5 and do any updates and return the new value. T prime has nothing, so it just returns back -5. Tells E that it's all -5. And just like before, E informs E prime that -5 is the left operand. And just like before, we first have to compute the right side of this addition operation. So E prime now knows that -5 is the left operand. So now it has to figure out what the right operand is. So T calls its child, which is F. F tells T its left operand is 2. And now T tells T prime that the left operand was 2. And T prime now has to recursively find the right operand for its multiplication. So its right child is F. So F consumes this 3 token and tells T prime that the right-hand side is 3. And now T prime has enough information to do the multiplication. So it knows that the left side was 2 because of its parent, and it knows that the right operand is 3 because of F. So now it can actually make a new operation, creates a new temporary variable and emits the operation. So I'll write the resulting code down here. So that's the first thing that gets emitted. And that's what we expect, right? We want, because of order of operations, we want the multiplication to happen first. So because T prime is the first in this tree to find the complete operation, find both the left and right-hand side, it emits T1 first. Okay, so then what's next? What is T1, after T prime returns, what happens when that returns?
We passed T1.
Good, yeah, it returns T1 because T1 is like the value of T prime. T prime discovered that its value is T1, whatever is going to be held in T1. If we're writing an interpreter, just, if you're doing that like postfix notation computation, you would just do the actual computation 2 times 3. But our compiler is generating code that does the operations. And the way it handles intermediate values is it just represents them as some new temporary variable. It has control over temporary variables. So it can just make a new one and tell its parent that instead of a number being its value is a variable, T1. With me so far? The questions on that? Make sense? Yeah.
Wouldn't it want to pass it to the next one first?
Oh, yep, you're right. Thank you. Very good point. So T prime computed T times 3, but because there may be a sequence of operations at the same precedence, it passes what it thinks what its value is to T prime, and T prime has no operations underneath, so it just passes T1 back. That's still the value. Yeah.
So if you did have an operation,
Yeah.
like T1 plus, or
Yeah, yes, exactly. So let's use green here to speculate. So if T prime was instead, let's say T prime was multiplication F. Let me do my speculation over here. So let's say it was times F T prime, and F turned out to be like 4. Then yes, so T1 would be passed to it. Let's use a different color here. So T1 would have been passed to F, and F would have, no, that's not right, sorry. So it would have found that f tells t prime that its value is 4. And then t prime would have emitted a new operation, t2 equals the left side, which is t prime, times the right side, which is 4. Does that make sense? So if this little speculation in green had happened, then we'd have a different t2. We'd have yet another operation after it. And then t would instead pass back t2. Make sense? So I'm gonna erase that to make it slightly less confusing.
Yeah, this makes a lot of sense. This is actually like,
Okay, so t prime indeed had no syntax, so its value remains t1. Okay, so we're back on t prime. T prime has emitted this operation, t1 equals 2 times 3. So what does t prime pass back to t? I think we already went over this. Pass back t1 because t prime found that its computed value is now t1. T has finished computing the multiplication, so it returns its result back to e prime. Its result is t1. And just like, if you had operators of the same precedence, e prime would have to tell e prime what the left-hand value is. In this case, it's t1, but e prime, again, has no syntax underneath. So it just returns to its parent that its value is still t2. Okay, so now we've got e prime finally, I'm sorry, why did I say e2? T1. So it remains the same. Okay, all right. So what happens now? E prime, we're back at e prime. What happens at e prime? What is e prime's job now? Yeah, e prime's job is now to emit its addition. So it knows its left-hand operator because e passed the left operator to e prime, and e prime did all this work with its child, or it passed off this work to its child in e prime to figure out the value of the right-hand side of the operation. It turned out that was a nested operation, so e prime doesn't care. It just says, go out and give me whatever your value is of your side of the tree. And whatever value is passed back to it, either whether it's t1 or a number or any variable, it'll just say that's my right operand. So this kind of, and actually when you if you have job interviews and they ask about recursive programs, or you're working through some tricky algorithm that's recursive, this kind of illustrates one of the hallmarks of recursion, is that you can you can break the problem down into individual pieces and write one function that just solves one problem and then just sort of recursively passes off the rest of the problem to its other child. So like dynamic programming problems are like this, where they're kind of breaking the problem down into smaller pieces. So e prime here doesn't have to do anything fancy at all. It just says, I know what my left operator is, and then it just calls a different function to say, give me the right operator. So e prime doesn't care at all what happens in the rest of the tree. Its logic is always the same. It says, I'm going to call t to do the job for me, to get the right operand. And as soon as I get that, I'm just going to emit my addition. So it needs no more information than that. And what makes this a little trickier than normal recursion, the kind of recursive algorithms you might be used to, like post-order traversals, is that there are multiple interlocking recursive functions here. So e prime and t are different recursive functions. So they have to kind of have to work together they have to be able to be composed together. So T1 does a very specific job. It has a very specific input and output. E prime expects a very specific output from T. And so you kind of show the composability of these functions as well. Anyway, just a little aside on some philosophy about recursion. But anyway, E prime knows its left-hand operation. It knows its right-hand operation. So it does just what it did in the last tree. It creates a new variable and emits the operation So it knows that -5 is the left-hand side and T1 is the right-hand side. So it emits the operation to its output. Okay, questions on this so far? Yeah.
When you say it didn't beat output, do you mean just as is, like you're writing, or?
Well, so I'm writing in a kind of idealized machine code here, but you would be outputting LLVMIR, the LLVMIR equivalent of this. I mean, you could output this and then translate it later if you really want to, but yeah, you can just directly out, like literally just print out LLVMIR. Yeah, you're just literally printing it out in order, just like a post-order traversal, except, so post-order traversals, usually you think of printing for post-order traversals, but you can put those tree traversals are kind of like templates for any kind of recursive problem solving. So parsing is a kind of recursive problem solving where instead of printing out the node itself, you do a little extra processing like printing out an instruction instead. Or if you're doing merge sort, doesn't just do a traversal, it also merges the arrays. So those like traversals, they're kind of like fundamental computer science. If you kind of can work with those really well, then you can actually do a wide range of recursive problem solving. And it's convenient because if you can break the problem down the right way, then it makes actually very simple code to write. So yeah, you just literally print F. Emit just means like print F. It's a fancy word for just printing the code. And I wrote this in the order in which those emits happened. So as it turns out, it's the exact order we want. It's the order of operations. That just falls out of the tree structure. Just directly falls out of it. All right, questions so far? Any other questions? Pretty straightforward now? Makes sense? All right, I dig it too.
Sense, yeah.
All right, and finally, E prime, it constructed, its value is T2, so it tells its parent what its final value was, and then E can finally tell its parent that the resulting value was T2. And so its parent would be its parent would have been a print statement, or a statement rather. And so, to sort of complete this a little bit, the statement gets passed to T2, and then what code does statement emit? Yeah, call void. It emits the print. And print just takes the variable. So now this is actually even like simpler than Project Zero because all statement does is just pass all the work onto expression to say like, you give me what the final value is going to be. I don't care what it is. You tell me what it is. And all statement has to do is say, is this a print statement? Okay, call it and just plug in the return value of E prime. Or of E, I'm sorry, of E. Statement has to do it.
Well, yeah, because if you attach it to the E.
If you attach it to E, then E is, yeah, I mean, yeah. And later on, expression is going to be used in other statements. So it's not only going to be a print statement in later iterations of this language. Questions on this? Questions? Yeah.
So, like, in case we have like
parentheses, yeah.
Yeah, like object 2 and
So let's quickly look at parentheses. Let's see what happens when we have parentheses. So I'm not going to do the full correct. Oops. Good. So this is what will happen if we've got parentheses. There's going to be some big tree down here. That looks very ugly. So this is going to be some massive tree, potentially. And F, so what is F? F is only a child of, well, F can be a child of either of these things. But let's assume it's a child of T. And T has its own, tree above it. Okay, so what happens when code generation, when we've got this when we got these parentheses. So what does E return? Like up here,
The right goes up to you.
that E could be this top E here. It just returns the value of that entire expression.
Yeah, the right goes.
So if E happens to return T2, that T2 just gets passed to F, and now F's value, instead of F being a number like on all the examples we saw, F is just a variable instead. And it fits right into our whole scheme. So here, for instance, if F returned a variable, it would be no different for the rest of the computation. Because each one of these functions expects a very specific thing from all the functions that it calls. And they all just kind of compose together in a kind of beautiful interlocking algorithm. Make sense? So actually, once you have the expression done, adding parenthesized expressions is just trivial. It's just literally calling expression and returning its value. Makes sense? Any other questions? So should I show some pseudocode, or should we just leave? Should we just leave early? We have 2 minutes.
I mean, pseudocode would be great.
I mean, it's kind of in the slides actually.
Yeah.
I wrote in the slides, so you can kind of figure out the rest. You can figure out that factor part. But this should make a little bit more sense now. Why expression is reading left and passing it to expression prime. Why expression prime is doing the emission and then passing its value onto expression. No, I missed something here. So this actually has to return as well, but yeah, I'll fix that for you. All right, so let's leave 2 minutes early, and let me know if you have questions, and good luck on your homework and your project.
Mine's about the spacing test. What would have caused me to fail that?